I will be showing you how you do an analysis for an aspect ratio 12.7 tapered wing. So, going to open the project. So basically, you first go to Direct Foil Design, go to Foil, Macro Foils, and add the 4412 foil, and it's already been added. And after that, we go to the XFLR Direct Analysis, and we have to do a batch analysis. So we do Reynolds number from 300,000 or 100,000 to 3 million. The Reynolds number that the airfoil is at is going to be 2 million because the chord length is 1 meter. The free stream is 30 meters per second. If you use the Reynolds number equation, you get 2 million from that. So to be on the safe side, you go to 3 million, and then I went all the way down to 100,000. And then we do an analysis from -5 to 20 at an increment of 1. And so that gives you the batch analysis, and this is the only way that you're going to be able to analyze the wing, because if you don't have this batch analysis, it doesn't have data. So in order to analyze the wing, you're going to go into module wing and plane design. So you want to make a new plane, but I already made the tapered plane. And so you want to deselect elevator, fin, wing 2, and body. So we want to define the main wing, and the root chord is 1 meter, and because it's tapered at 0.7, the tip chord is going to be 0.7, and the offset has to be set to 0.150 to get rid of the, make it evenly tapered. And so the wingspan has to be 10.2. In order to get an aspect ratio of 12, you use the span equation for a tapered wing is equal to 1/2 wingspan times the summation of the tip and root chord length. And you just solve for the span. You get 10.2, and then you divide by 2 because this is going to be symmetric. And so once you have the wing, you want to go into analysis, define an analysis. You want to use the type 1 fixed speed at 30 meters per second. And for analysis, you want to use lifting line theory. And then after that, you go into analysis settings, start at -5 to 20, and then analyze. After that, you get all this data at the different values. Then you can export the results. It gives you a CSV file that you can get, and this CSV file, you just copy paste the data into a main Excel file. And in order to get the lift curve slope for the wing, you want to go and select the AOA, the CL, and you insert a chart. Then you go right click and add a trend line and display the equation, and this slope is the lift curve slope of the wing. And to calculate theoretical values, you want to use these equations. A equal A naught 1 plus A naught over pi ER, and E is the span efficiency factor, and it's given by delta. And to get delta, you use this figure. So because we're at taper ratio 0.7, we go up until we hit AR equal 10, and then we match it, and we got a delta of 0.05 for this wing. The reason why I'm using AR equal 10 instead of AR equal 12 is because there's no AR equal 12, so this is the closest to it. And I input these equations into this Python script, and so this just calculates the theoretical lift curve slope for the wing given the aspect ratio and the delta, and it gets a close value. If I run this for tapered AR12, I get 0.0933, and in the Excel file we get 0.0936. So they're very close. And to determine and tabulate the maximum CL, CD, we just go here, we use an equation, divide CL by CD, then apply it to everything else. And here, we use the max to find the max of this one. Then we just search for where this appears, and it appears here. And this is at a AOA of 2, so that's how we determine the max CL and the corresponding max CL over CD and determine the AOA. And using the overall lift coefficient at angle of attack 5 degrees, we get the overall induced drag coefficient, induced angle of attack, effective angle of attack, and downwash velocity. So we use the equations we found in class. And so these are the equations. This gives you induced coefficient of drag. This gives you induced angle of attack. This is effective angle of attack, and this is the downwash velocity. So I put these equations into the Python script. So I just run this, and I have the lift coefficient inputted here. If you look at the Excel file at 5, this is the lift coefficient, so I just put it in there. So I run it. I get these values for the induced drag coefficient, induced, effective, and downwash velocity. And for the effects of a higher taper ratio, you're going to see that when you have a higher taper ratio, that increases your maximum CL over CD. As you can see for the tapered, it's right above the rectangular AR12, so it's slightly better than the non-tapered. So the higher your aspect ratio, the higher your CL over CD max is, so it gets you more lift, and it also reduces your induced drag coefficient, because if you look at the equation for induced drag coefficient, the higher your aspect ratio, the lower your induced drag. And the taper ratio also reduces induced drag, because if you look at the chart for taper ratio, this delta decreases, and it means your E is closer to 1. So as you decrease the taper ratio, making the wing more tapered, it just means that your delta gets closer to 0, your E gets closer to 1, which means you're closer to an elliptical loading, and that means that your induced drag coefficient also decreases. So that's what the parameters do to the aerodynamic performance of the wing.